So in this video, I'm going to talk a little bit about topic 9.3 and looking at some double slit interference patterns, multiple slit interference patterns, ultimately getting to the diffraction grading. I'm not going to talk about the second half of topic 9.3 that has to do with thin films. That's really something that is hard to do over video without some really complicated animations that I don't have. So I'll have to do that with you in class. In terms of what we're looking at for outcomes, we're hoping to do something very similar to what we did with diffraction in topic 9.3, which is to understand where the pattern of maxima and minima is coming from. It's a different pattern for a double slit than for a single slit, but a similar derivation to explain it. We'll want to understand how slit width and spacing and the wavelength of the light affect that pattern, and look at the impact of diffraction and multiple slits on the double slit pattern. Again, here, if you've just come from watching the topic 9.2 video, we're looking at continuous interference. I'll refer you back to the topic 9.2 video to go through this slide, but just reminding you that when the path length difference is 1 or 2 or 3 wavelengths, there's constructive interference. When it's half, 1.5, 2.5, there will be destructive interference at all points in time at one particular location. So the double slit interference pattern we're seeing here, the photo in the bottom is similar to the photo that we see in topic 9.2 for diffraction, but this one shows interference. And in the bright spot that we have here in the center, we see these very evenly spaced maxima and minima, the bright spots with the dark lines. We do notice some behavior out here that looks a little bit funny, like there's something where it goes away and then it comes back. More on that later. That has to do with diffraction. But to generalize it and maybe looking at a simulation that you can play along with here, the pattern shows equally spaced a large number of maxima and minima, and the one in the center, unlike with diffraction, isn't particularly different from the ones that are along the side. And we're going to understand these peaks as having to be the places where from one slit and the other slit, there are equal path lengths so that we have constructive interference, or differ by one wavelength, so there's constructive interference, different by two wavelengths, so that there's constructive interference, or in these dark regions where there's continuous destructive interference, where there's a half wavelength or 1.5 wavelength difference. Also notice here that the central maxima isn't really particularly large. It's also not particularly wide. These are all equally spaced throughout. This is known as the Young double slit interference pattern. And it arises because we have very narrow slits where there's a lot of diffraction spreading the light out, but the light from the left slit, which is spread out widely over a screen, and the light from the right slit, which is also spread out widely from the screen, travel slightly different distances to reach the screen, and so they will interfere. The interference fringes tend to be evenly spaced. They're evenly spaced in angle. You could write this as theta is approximately equal to lambda over d, or you can write it spaced horizontally as S is equal to lambda large d, which is the distance from the screen to the slits, divided by small d, which is the spacing between the individual slits. And we'll look at a derivation of that in a moment. Right now, in fact. Sorry, I'm coming off the screen here. The geometry for this looks very similar to the geometry for the single slit diffraction. So I will go through this one a little bit quicker. You really should go through 9.2 if you haven't yet. The key thing here is that we have a pair of similar triangles from the middle of the upper slit and the middle of the lower slit. These are separated by a distance lowercase d, a distance capital D away from a screen, and we have a distance y along the screen that shows us whether we are going to be at a location of a minima or a maxima. But the angle theta in this triangle that is made up of this path length difference delta and side length d for the separation of the slits is a similar triangle to the angle theta with y and d. So similar triangles, especially with small angles, give us that delta over d, the path length difference divided by the slit separation, is equal to y over d. And we're going to try to use this to find out the angle from the center of the slit to the location of the first maxima and also to the first minima. And everything is going to be referenced to a straight line that leaves in between the middle of the two slits and will be located at the central maxima. Before we go into this, let me just make sure that we understand why there is a central maxima. The distance that the light travels to get from the top slit to the midpoint and the bottom slit to get to the midpoint is always going to be exactly the same. So you will always see constructive interference. This is very similar to the origin of Poisson spot, the Fresnel spot around a circular disk. Where do these other maxima come from, however? Well, in this diagram here, and this one is actually going to be simpler than what we had to do with the diffraction, there are two sources of light. There's the source from the top and the source from the bottom, separated by distance d. Looking at the angle theta that leads us to the first maxima, this angle theta here defines a relationship between d and the path length difference delta. As long as that distance is equal to a multiple of lambda, and for the first interference maxima away from the middle, this will be n is equal to 1. We get constructive interference whenever n times lambda is equal to d times the sine of theta, d sine of theta being the path length difference here. This is a really good formula to keep in mind. N lambda is equal to d sine theta, tells us the location of all of the constructive maxima. We don't usually do a small angle approximation with double slit interference because the patterns generally extend well beyond 10 degrees because the slits are very, very narrow and we see a lot of diffraction and we see larger angles. So we don't usually use a small angle approximation. Of course, the same argument can be used to find the minima. That's going to be where there is destructive interference, and the path length difference is not going to be an integer number of wavelengths. It's going to be a half integer. So half lambda equals d sine theta. 1.5 lambda equals d sine theta gives us the destructive locations. And of course, this is exactly the same as was described here. The path lengths are equal. That's n is equal to 0. The path lengths differ by half a wavelength, n plus 0 plus a half. They differ by one wavelength, n is equal to 1, etc. We can do a small angle approximation if we want to, and we can then find the locations of those maxima and minima. They're going to end up being very similar. Some key observations about the Young double slit interference pattern. One is that diffraction is really necessary here. If the light that's passing through the two slits is not spreading out, and you just get 1 point of light behind one slit and 1 point of light behind another slit, then there's no place where the light from both slits is reaching simultaneously, and you can't have interference. Usually, what we're thinking about is when we have very, very large diffractions, so very, very narrow slits, meaning we're in that extreme case where the two slits act like point sources of light, and all of the space on the other side of the two slits can be reached by light from both the top source and the bottom source. And so the only role that diffraction plays is in spreading the light. In a little bit, we'll look at what happens when the slits are a little bit wider and diffraction minima play a role as well. The other thing that's important is that we assume that that the light that's coming through both slits is in phase. There are experiments that you can set up that put an intentional phase difference between the light from the two slits. And when that happens, the central won't necessarily be a maximum. the fringes can walk a little bit to the left or to the right. So you could actually have a minima if the light was exactly out of phase, that there was a pi/2 phase difference between the light from the top slit and the bottom slit. I mentioned that the main thing that we think of is diffraction spreads the light out very, very far, but it's also possible that those slits can be a little bit wider. We'll look at these pictures that are frames from this animation. First, we'll look at the animation itself. So this is an example of what we see for the double slit diffraction pattern. There's no effect of diffraction included here. And so we can see what happens as we increase the wavelength. We know that n lambda is equal to d sine theta. So as we increase the wavelength, that's correct, we increase the spacing of those fringes. Here it's changing the color to show the color of light that we're using. On the other hand, if we increase the distance, or sorry, whoops, it's in the end right now. If we decrease the distance between the slits, we'll also spread this out a little bit. So increasing the wavelength increases the spacing of the fringes. Increasing the distance between the slit decreases the spacing of the fringes. Let's go to something like, let's go to green light here. When we let's go with a very narrow slit and now include the effect of diffraction. Notice that with a very, very narrow slit, as small as the simulation can go, the addition of diffraction doesn't include or doesn't change anything. However, as the slits start to become wider, we'll see this envelope change, the envelope being drawn in black, until we get to the narrowest slits possible. And we can see that now the diffraction pattern gives a minimum, and the interference pattern is no longer nice and simple. It's modified by the diffraction envelope. Let's go back. So you have the evenly spaced peaks. Maybe I'll bring this wavelength down a little bit so we have more peaks to look at. So you have the evenly spaced interference fringes, but when the slit width gets bigger, the diffraction envelope and the diffraction pattern modifies that. The central maxima stays the same, but the successive maxima become much smaller. And in fact, in some places, you actually can't see any light, even though there should be a maxima there. Let me put my mouse over it so we can see one of those happen. Here we see an interference maxima, and watch that point as the slits get narrower. As the slits get narrower, we can actually make it so that that maxima falls at the same place as the first diffraction minima. And so there's this very interesting interplay between the spacing of the slits, which changes the spacing of the interference fringes, and the size of the slits that changes the diffraction pattern. And of course, the wavelength can also adjust, and that adjusts both patterns at the same time. Both diffraction and interference depend on the wavelength. So what are some of the things that we notice? Well, what we notice is that the pattern that we get is the interference pattern modulated or modified or multiplied by the diffraction pattern. Let's take a look at some specific screenshots and examples. In the top here, we're looking at the narrow slit and behavior. The envelope for diffraction is very, very slight. There's not much change associated with it. And so the interference fringes look like they're of the same intensity, and of course, they're equally spaced. As we go to a slit width that is wider, now the diffraction pattern becomes substantial, and the intensity of those maxima becomes weaker and weaker as you go away from the central maxima. Notice that that affects the blue light faster than it affects the red light. And then finally, we have, as you go to particularly wide slits, if they're about half the width of the spacing, you have a very strong central maxima from diffraction, and only inside of that strong central maxima do you see interference fringes. So it ends up becoming quite difficult to think about that pattern. And I'm going to just go back to the first picture we looked at for interference. Here, a red laser being shown through a pair of double slits. And we see actually the interference pattern, those narrowly spaced fringes here, being modulated by the diffraction pattern. High intensity central maxima, first minima on either side, and then those secondary maxima where the interference fringes continue, but they're at a much lower intensity. We can still see them. So it's a more complicated pattern. Oops, going the wrong way. And so we have that modulation included. Another thing that we can do is we can look at the effect of adding additional slits that are at the same spacing. So instead of having two slits, and here we have our diffraction modulated interference pattern, we can have larger numbers of slits. As you do that, you end up seeing some new features. The maxima become higher and sharper. They're no longer sinusoidal in shape, and we get these secondary maxima that are there for each slit beyond 2. So this is a 4-slit interference pattern, and this would be a 6-slit interference pattern. Notice that the spacing is the same inside of that central maxima, which goes from minus 20 to plus 20. We have 1, 2, 3, 4, 5 peaks. Still from minus 20 to 20, 1, 2, 3, 4, 5 primary peaks. Still 1, 2, 3, 4, 5 primary peaks, but they become much larger in intensity, and they become much narrower as more light is focused into these narrower peaks. Another simulation here to play around with. I'll just show a couple of quick examples here, assuming this one loads pretty quickly. So here we have number of slits is, say, 2. If we go to 3, we get 1 secondary maxima, 4, 5, 6, 7, 8, 9, and 10. So these peaks are getting much, much narrower. Worth playing around with because you can also adjust the slit width and the slit spacing. Where does this come from? When we add the intensity piece, we can come up with from thinking about what happens when we add a third slit. If we think of the amount of light that's coming through each slit as having an intensity of 1, then when we have 2 slits, we're going to have an intensity that is 4 times larger than the single slit. 4 times larger because if you double the amplitude, you get 4 times the intensity. If you add a third slit, you'll have 3 times as much light as 3 beams interfere constructively, 3 times the amplitude, 9 times the intensity, 5 times the amplitude, 25 times the intensity. But so at your same space where you had, say, green and red interfere constructively, when you add blue, it's equally spaced, so it's also going to be interfering constructively. The path length difference between red and green is 1 wavelength. The path length difference between green and blue is 1 wavelength, and red and blue is 2 wavelengths. So those are all going to interfere constructively. So we're going to get these bigger, stronger peaks. Why the secondary maxima? Whoops. Well, if we look at the secondary maxima, that one is at a place where there would normally be a minima. Red would interfere destructively with green. These two are going to cancel each other out, but blue is still sending light to that point. So that creates this little place where even though the light from 2 of these is canceling out, the third slit is still providing light there. Another way of thinking about it is that red and blue are spaced further apart, so they're going to create a constructive interference peak here, and green is going to take away some of it. So that's a secondary maximum with an amplitude of 1. As you get to more and more slits, this becomes much more difficult to work with. But the main thing is that we know that constructive interference is going to occur at the same location. You will have secondary maxima until they become almost undetectable with large number of slits. And the intensity of that central maxima is going to go as the square of the number of slits relative to the intensity of light coming through one slit. So that's what happens with multiple slits. Doesn't change the spacing, does change the intensity, does change the sharpness. Going to the limit of multiple slits, we have what's known as a diffraction grating. A diffraction grating is a very, very, very finely etched surface that has slits that are evenly spaced, and it's defined by the number of lines that you get per millimeter or the number of lines per inch. A single laser beam might hit dozens to hundreds of lines, and so the interference peaks are very, very sharp. The slits are very, very narrow, so diffraction is very, very large. And with a diffraction grating, you will see just very sharp individual peaks that are spaced evenly in angle. N lambda is equal to d sine theta. But you won't, and they'll be spaced over a very large angle. And so this is what's known as a diffraction grating. They're excellent tools for helping us measure the wavelength of particular colors of light. We'll talk more about them and their use in topic 9.4. I'm going to pause here. Oh, no, I have one more slide. When we do with problem solving with interference patterns, it's important that when you look at, say, a graph, you are distinguishing between diffraction from the individual slits and interference from the different slits. In a picture like this, for example, the envelope is the blue that we see here in blue is related to the diffraction from a single slit. So the location of that diffraction minima tells us something about how large each individual slit is, whereas the spacing of the interference fringes is telling us something about how far apart the slits are spaced. And we can also use this to look at the intensity to help us learn something about how many slits are there. We can see the individual, the sort of secondary maxima. We can work with counting those as well. That's the first half of topic 9.3. We'll continue with thin film interference, which is beautiful, but rather difficult in class in person.